Welcome to the first International Symposium on Quantum Computing and Musical Creativity. This is research paper session 3, and we'll be kicking it off with our very own Paulo Itaborai, and he'll be talking about quantum audio representations.
Okay, thank you, Suchitra. Let me share my screen. Okay. Now, hopefully everything is right. So, thank you everyone for your time. I am Paulo Itaborai, as Suchitra introduced me. This work is a collaboration with Professor Eduardo Miranda for the QTune project. And it's about quantum representations of audio. We have seen many talks here at the conference, and we'll see probably many interesting talks later about how to map quantum information back to the classical domain, and then use it as a control parameter for some types of digital synthesis. So you have your kind of synthesizer, and then you just try to work with your quantum computer in a control manner. You use this quantum information that way. I got interested in exploring how can we actually put audio files inside the quantum machine. That's what generated this work, which is a survey of different types of representations and encoding schemes for audio on quantum computers. So we have this very nice image at the beginning, showing our current status of audio frameworks. We have our mechanical audio wave being played by some type of instrument. So, and then you transform this with some transducer into analog signals, which are really oscillating voltages. Then you use some type of circuit, electrical circuit, to transform this analog signal into pulses, and then transforming this into digital information that can be read by a computer, a classical one. And then now we can maybe try to understand how can we build quantum circuits and make quantum computers understand and store our signals. So let me, no, of course, this work, I think I've mentioned already, this work is a part of the QTune project at the ICCMR University of Plymouth. So the main objectives of this work was, as I said, learn how to encode raw digital information, audio information into computers. And this will be really useful for future quantum technology that will be able, well, if you know how the impact that the ability of storing quantum digital audio had for our synthesizers and DAWs, I think that this will have the same impact for quantum audio. Then we have the layer of really understanding and making a survey of the existing quantum representations of audio. And maybe the most important part of this work is really to congregate all of this information and make it accessible for the DSP, digital signal processing community, the audio computer music community, people that are on the classical fields, and they are trying to enter on the quantum fields and understand how can this be done. And maybe audio is a good way to introduce these people to that kind of thing. And of course, I can try, if I have time, to show some experiments that can be done with near-term computing. So that's a very nice timeline. What do we have here? This is, let me start by saying that we have a very curious timeline of quantum audio representations, because you can see that first we had actually an explosion of papers talking about quantum images, but we lacked for a long time any literature about quantum audio. So if you can see, we had first until 2013, we had only quantum image representations, of course, formalized. Of course, there were some people that were working, were trying to load audio files, but nobody really tried to formalize and put that in a paper. That happened for the first time in 2016, so just a few years ago. And then it evolved from then. So we are now currently in the quantum audio explosion, or maybe the quantum audio golden era. And the interesting thing is that many of this quantum audio, of course, they were derived and they learned a lot from these quantum image representations. And really they are the analogous, the correlate of these quantum image representations. And so if you go to this literature about quantum images, you can actually learn about a lot about quantum audio, of course, with some differences. So let me just go through every paper here. First, we had this qubit lattice proposition by Venegas, which I won't go deeper, but it was the first paper that I've encountered specifically talking about images in quantum mechanics. Then we have this very interesting paper called Image Compression and Entanglement, which proposes this representation called RealCat, which is simply putting everything in a superposition. Then a few years later, we have the flexible representation of quantum images proposed by Lee, and in 2011. And this was really a breakthrough on quantum images. It optimized many things and made some fine control possible. Then we have 2 years later this novel enhanced quantum representation of digital images, which stores information in binary integers inside quantum states instead of the probability amplitudes. And then we have a multi-channel version of this image, so a video, or maybe a GIF. Then we had in 2016 the first representation of digital audio. I think Scott has mentioned this representation on his paper, on his talk yesterday. This representation is derived from the Necker representation. I'm going to talk about that in more detail. Then we had a small correction of the QRDA, and this became the most consolidated quantum audio representation, which is the FRQA. And then we had two other papers that are really similar. They really discuss the same type of representation, which is the FRQA, but interpreting the binary integers in a different way. And of course, we have a multi-channel version of this representation as well. So I have this summarized in a table, and I can show here how the quantum images have influenced the quantum audio representations historically. And we can clearly see that there is some kind of gap still on the propositions of quantum representations, since these were proposed later in the timeline. People already started to explore quantum audio using the Necker image representation, which is very good. But I felt like we should maybe fill in this gap and just have everything together. Maybe we can explore these representations in an artistic way. Of course, there is a lot of possibilities for all kinds of representations. They all have advantages and disadvantages. So RealCat doesn't have a formal audio representation, neither FRQI. You may also notice on this table that the FRQA is not derived by FRQI, which really bothers me, really confuses me, So one of the things that I'm trying to propose on this work is to actually rename this representations and have a more unified terminology for them. Okay, I'll explain that in more detail. Maybe I can try just to simplify things, but you actually have to know, now you have to know more acronyms, but well, we can try with both systems, naming systems. So the idea is that I've tried to just put together the RealCat version of audio and the FRQI version of audio, and I call this KeyPen and SQPen. Of course, I'm saying that later. And then I've changed these names into the KeySM acronym and its variations, and then a multi-channel version of the KeySM. Let me go further into these acronyms. This new naming system is really about trying to bring this terminology back to the audio community. And if we can see that many encoding schemes, many ways to encode signal information, both in analog and digital systems, use this modulation radical. And I thought, well, we could do the same with quantum audio. So we have, of course, amplitude, frequency modulation that we can listen on radios, and we have pulse code modulation, for example, that is very popular with digital audio. So I think we should do the same with quantum audio encoding schemes, and then maybe call them in a way that we can understand which part of the quantum state that we are manipulating. So, for example, we can maybe encode information in the probability amplitudes, or maybe we can use really a combination of multiple qubits in a binary state. So let me formally introduce these new naming systems for quantum audio representations. We have the RealCat version of audio, which I've called the quantum probability amplitude modulation. This is simply a quantum superposition. We have this one that is called single qubit probability amplitude modulation. I will explain this in more detail. Then we have FRQA, which I am renaming as quantum state modulation. Okay. And then we have all of the remaining state-based representations being just also being a quantum state modulation, but the interpretation of the binaries change. The other important thing to really formalize RealCat and FRQI is that they are a completely different form of encoding scheme, in which you use probability amplitudes. They are really a very quantum paradigm of understanding information, in contrast to the quantum state modulation, when we really are getting binary data from the computer and trying to put that in a quantum state and look, oh, this quantum state has exactly the same binary data. So it's a very different paradigm. So of course, maybe I'll just reviewing this is a digital audio. We have an analog signal, and then we just take a lot of photographs through equally spaced photographs through time, and then we look at the amplitudes at these timestamps, and then we just quantize these amplitudes back into some binary information that the computer can read. For example, we can use an integer for making this quantization, or maybe an integer in a signed, the two complement scheme way that we can represent negative numbers. That is the main difference actually between quantum audio and quantum images, as quantum images range from 0 to 1, are signals that range from 0 to 1, but quantum audio has this -1 to 1 range. So that's the important difference about these representations. And of course, the dimension. Images have two dimension. All of these quantum audio representations, they encode time information in the same way. You just, so for example, if you have your audio signal and they are indexed for their timestamps, and the idea is just that you put all of the amplitude information in parallel in an equal superposition in the time register. So you turn this time index into a time quantum register. Then you put that quantum register in a superposition, and then you use some type of encoding scheme to insert the amplitude information correlated with that time space, and instead maybe entangled, maybe as a probability amplitude. So the RealCat version that I've called QPAM is just a simple superposition in a way that we store the information, the raw information into the probability amplitudes of the superposition. Of course, we need to make some shifting and some scaling to our audio samples in order to really have something that is normalized and that we can really interpret as probability amplitudes. So that's what this alpha equation is doing. Another important thing about this notation is that I am intentionally using capital N, which would be the size of the audio instead of the number of qubits, which would be 2 to the power, which would be this end. So capital N would be the 2 to the power of n, meaning that we can only store powers of 2 sized audio. And if you don't have this kind of audio, you can always insert a lot of zeros until you reach the desired size. Okay, so yes, you really, this is just a simple superposition. A circuit for this is really just an initialize function, an initialize gate. Just get all of your probability amplitudes and say, please put me in that quantum state, and that is the quantum audio state. And for retrieving it is just you run the secret circuit several times, and then you look at the statistics, and this will hopefully look similar to our audio. So you can see that we have our original audio, and then we have the result of our experiment. These have the same, roughly the same profile, and this can be converted back to a digital signal, which is the black line here. You can see that the QPAM doesn't really have a perfect retrieval strategy, since this is purely statistical, pretty probabilistic. So you can maybe make more and more shots on your quantum circuit until you reach an acceptable error range. I have actually implemented some functions for really preparing all of these encoding informations in Python, and using some kinds of, and this is the actual implementation of QPAM. Is just an initialize function in Qiskit. Okay, so now let me explain the SQPAM, which I call single qubit probability amplitude modulation. This is also a probability amplitude based encoding scheme, but the main difference is that you have an extra single qubit register in which you are going to encode the amplitude information, and then you are going to entangle that amplitude information to the respective time index that this amplitude information is related to. So for example, if I can convert these digital audio amplitudes into some range, for example, between 0 and pi/2, I can use this qubit. I can use look at the possible real value numbers that I can use as probability amplitudes, and store this in this way on the single qubit, and you can see that each amplitude is entangled with a time index. How do you actually set these amplitudes, these angles? You have this. So if you need to learn anything about this presentation, is this slide, is the value setting operation. The idea is that you have some gate. This gate is responsible for setting the amplitude values on your register. It can be anything depending on the representation, but the important part is how do you entangle amplitude information to time indexes. So you have, for example, this time register. You put that in a superposition using Hadamard gates, and then you just put a bunch of multi-controlled gates for doing the fine value setting operations. So for example, for this operation is waiting for when the time state is at the 0, 0 state, so then it can set the operation, so it can set the amplitude at this timestamp. There is also an implementation in Python of this. I can show you later. And this is a typical retrieval histogram when you actually run the circuit. The idea here is to look at the even beams of this representation. This means that we are looking at the sign coefficient of the register. So we have the cosine, the sine, cosine, sine. If you look carefully at the even beams, you can actually see the audio profile that we have on the right. Last but not least, we have the quantum state modulation. And the idea here is to actually use another full quantum register and then use the qubits as binary data and have, so you have an audio and you use the binary information from that amplitudes, and you can encode that directly into a quantum state, and then you just correlate this quantum state with the timestamp which it is meant to be. The value setting operation for this is similar, but instead of having rotations like the ISQCMC, you have just multi-controlled NOT gates. So for example, if your amplitude is 111 at some point, you need to set all of the amplitudes to 111 and so on. Another Qiskit implementation. And the idea of this histogram is that you're not changing the probability amplitudes anymore. So you should have an equal superposition of all of the possible states that you have prepared and nothing else. Of course, this is an ideal setup without noise and decoherence. But when you do this on simulation, you have the superposition, and the only states that are can be possibly measured are the states which have the timestamp and the corresponding amplitude. And this is a perfect reconstruction of the audio signal. How am I good on time? Okay.
Yeah, 5 minutes.
5 minutes. So I'm just going to jump. There are some basic operations that were proposed, like concatenation, addition, delay, inversion, something like that. And I have found some very interesting paper about quantum images, which are trying to do some parallel comparison. I can show you later. And well, how can you actually apply this on a real context? You can use some wavetable synthesis. Since these quantum audio circuits are quite large for our near-term systems, maybe it's a good idea to think in a way that we can have a small audio sample and then multiply that as an oscillator. So wavetable synthesis is a perfect way to do that. And you can do, I had maybe some examples that I could show you. So for example, you can use, you can have one period of an oscillator and then you encode this into your quantum machine as a QPen, for example. And then when you retrieve it, you don't retrieve exactly the same audio. It's not a perfect reconstruction. The auditory effect of this is some kind of dithering to the sound. It adds a little bit of noise. And of course, you can explore this artistically and maybe update this wavetable while the counts are being made, while the experiment is being run and the counts are being populated until the distribution resembles your original audio. And this is a very interesting effect that I maybe want to finish just showing this audio. Here I have, it's somewhere here. I'm going to show this. Did you hear that? Were you able to hear? Okay. So yeah, it's very interesting. So the idea is that you make some experiments with a different amount of shots, and you just update your wavetable as you change the number of shots, and this will make this kind of Geiger counter effect from the, which is very interesting. I can, well, this will be available later. I can make this available so I can show off. You can see all of the examples. And this was synthesized using a Python supercollider module, which can connect this with supercollider. And then I just implemented the wavetable synthesizer there and sent the results from Qiskit to supercollider. The implementation, you can actually experiment, you will be able to experiment with these quantum audio representations. I have implemented a small module that you can put an audio file, and he will retrieve a circuit that you can run and therefore insert some quantum audio into your quantum machine, into your local quantum machine. And I think that's it. So thank you very much. Do you have any questions? There are the references. And that's it.
Do we have time for questions?
Yeah, we can ask one or two questions, and then we run out of time, but so we could ask one or two questions that are in the Q&A there, and then we move on.
So we have a question by Nitika, who asks, can you speak a little bit about the advantages of using these quantum representations in light of fact that retrieving quantum information is harder than in classical due to no cloning, quantum tomography, etc.?
Okay, that's a nice question. Right now, of course, you don't have much advantages of just inserting and retrieving the quantum audio, because you have a lot of time for just and a lot of instructions just for preparing the audio state and then retrieving it back. But this is interesting because this is really a foundation to explore some quantum digital signal processing. And this can be advantageous in the future. For example, I can think in a way that you can really prepare a multi-channel audio state, and then you can run an analysis using, maybe you can make some kind of feature extraction and just run a few gates that will be parallelized, and this will be much more efficient in the quantum machine.
We have time for another question.
Okay, and this one is by Jim Weaver, who asks, how does the subset of valid quantum states constrain the audio that may be represented?
I think he's asking about the quantum state modulation, right? Let me think. So the idea is that the substate of valid states, they have a binary. You look at the state and then interpret that state as a binary number. So only the valid states have some useful information that you can actually turn back into audio information. For example, if you have a state like 100,000, it means that you have the amplitude correlated to 100 at the time 0. Does that answer the question?
I guess.
Okay, probably.
Yeah.
Jim can get in touch with Paul later and ask these more specific questions. I think we should move on, guys.